Welcome everybody. My name is Chris Peters. I work for a company called Data Minded. You can see it in the background. Data Minded is a data engineering company. That means that we build data platforms, data solutions, data analytics pipelines. Very much from a software engineering point of view. I've been asked by Martine, your professor, to give an introduction into modern data platforms and big data analytics. I understand most of you have a more or less technical background, so it will be a gentle introduction into all of these topics, and hopefully it's relevant for if you come into the professional life. Hopefully some of these things you'll remember and you can apply it in your day-to-day job. I was supposed to do this lecture in person, but as you all know, this got cancelled due to like the corona outbreak, right? So now we do everything through video recording. I don't do this a lot, so if things go wrong, if you see me fiddling with the controls, then be patient with me. That being said, let's dive into the slides. So, as I said, it's modern data platforms. I think in digital transformations we see in companies these days, data, as you all know, is becoming more and more critical. If you want to manage the data well, you also need something like a data platform in order to build all your insights. And we're gonna zoom into that today. Let's start with what is big data actually. What do we mean when we say big data? Well, there's quite a few definitions. I used to work in a large management consultancy firm, and there the main definition was that if it didn't fit in Excel anymore, then it's probably big data. That was true for that organization, but for most organizations, I like the definition the best, which is shown here. Big data is typically defined as the 3 V's. What do I mean? Volume, variety, and velocity. Volume is obvious, so that means you have a much bigger volume of data than what you're used to. And because of that, it's much more difficult to handle all these large volumes. Like the first data systems that were out there could only handle like kilobytes or megabytes of data. Now, when you build a modern data platform, you need to be able to handle gigabytes or terabytes or even petabytes of data. But there are 2 other dimensions to big data as well. One is velocity. With velocity, what we mean is because data comes in at a much more rapid speed, we need to be able to process it much more rapidly as well. So an example there is if you work, for instance, one of the projects we're doing is at the airport, and well, at the moment the airport is not seeing a lot of traffic, but on a normal day it's very busy, and we make a whole bunch of predictions in real time. Obviously their velocity is super important, because if we only make the predictions like, hey, we processed all the numbers of yesterday and now we can say that your delay will be this or that, that's too late, right? Velocity, like the timeliness of the insight is a big factor. And that's different because it used to be that a lot of the analytics was just batch. And if you processed it once a day, it was good enough, or once a week or once a month even. And then the third component of big data is variety. And what do we mean by variety is that if you look at analytic systems a couple of years ago, there were maybe 2 or 3 main data sources. You had your finance system, you might have an ERP system, and then that's more or less this, maybe 2 or 3 Excel files, and that was the sum total of all the data you had available in your organization. Well, today that's not the case anymore. Like, a lot of organizations have a lot of data, and a lot of it is unstructured as well. So that could be text files, it could be image files, video files, it could be anything, and not just unstructured, also coming from a lot of different sources. Like modern companies, they have like dozens and dozens of operational systems, and it creates a huge variety of data. And actually what we see in reality, like the volume of data, that's more or less a solved problem. We know how to deal with large volumes of data. There's tools and technologies out there, and we're going to see a few today. Velocity is also becoming more and more of a solved problem. It's a field very much in rapid evolution. But still there's tools out there to deal with the high velocity of data. But variety is still the main struggle for a lot of companies. Is that there's so much data out there. How do you organize that? How do you categorize it? That's a big challenge. So let's take a step back and think about what kind of analytics that companies do. Companies have been doing analytics from the very beginning. So this is an example of a financial statement from 1908. So that's more than 100 years ago. Financial analytics is a very simple but important form of analytics to do. We as a small startup, financial analytics is the most important analytics for us. So I need to know every month, like, are we making revenue? Are we making profit? Are we healthy? How is our cash flow statement looking like? So most analytics efforts in organizations, they started in the finance department because finance, as of day one, finance needs a view on the numbers, right? But that evolved towards more what I would call operational analytics. And this is an example dashboard of where you can see the sales per product line, maybe the discount on orders that you've given. So very much more tangible operational day-to-day analytics. But that also evolved, and it's nice to have dashboards like this, but more and more people want to get self-service analytics. So this is a screenshot of Tableau where you just give the data to the business users and they create their own insights. Very ad hoc, playing around with patterns or graphs they see and then applying that. And that's a big trend in the coming years, I think, is more and more self-service, where it used to be you had a BI department or a BI is business intelligence department, which did all the analytics for the rest of the organization. I think that's a bit behind us. Now everybody in the organization needs to use data. So data is being much more democratized. And self-service, Tableau, dashboards, or other tools, right? There's Power BI, there's Looker, there's a million other tools out there to do self-service analytics is the next step in the maturity. So you go from financial to operational to self-service analytics. As a next step, of course, there's only so much you can do with a dashboarding tool. So more and more we see companies hiring data scientists, and data scientists, they like to create models and predictions and things like that. They typically use Python, Jupyter Notebooks, R tools to let them explore the data and build deeper insights of what you could do in a normal dashboard. What we do see with companies often is that these data scientists are put in some kind of sandbox or lab. I think that's a bad trend where they say, we're going to create a data lab and they're going to experiment with new models or and very often isolated from business, so they're not too much disturbed by the day-to-day life. I think that's unhealthy. So as long as your algorithms run in a sandbox, they're not really adding a lot of value to the business, right? So the next obvious step is that your machine learning models, they do actually impact the business. This is an example of a website, I think is from Schoenentorfs, where you can see I browsed for one shoe, and then you see recommendations for other shoes based on the shoe I'm looking for. This is an example of a machine learning algorithm that trained somehow created recommendations for me, and live as I'm browsing the website, it put those machine learning results in my face, so to speak. That's an example of let's say machine learning in production. And obviously the final goal where some companies want to go towards, but I don't see a lot of companies there yet, is to have a fully automated AI, right? So think about investment banking, where they make automated trading decisions based on stock numbers and what have you. I'm not a stock trader, so I have no clue what is going on there. But in normal times, if all the stock markets aren't crashing like they are today, in normal times, it would make sense to have like some kind of automated trading robot that does all the investments for you based on certain parameters that you set, of course. So if we zoom out a bit, what is the trend that I've been describing here, and what is the pattern we see is that as businesses become more data-minded, their needs are shifting from more traditional reporting to machine learning and AI. And that's a trend that, because of that, the underlying data platforms shift as well. Whatever you do, whatever tools you use for financial reporting are probably not the right tools to use for machine learning algorithms, right? And we're going to zoom into that a bit. And let me start by explaining what is actually a data product. It's a new term being coined around. A data product, there's one definition here by DJ Patil, who used to be the chief data scientist of Barack Obama. And he says a data product is a product that facilitates an end goal through the use of data. That's still very vague, so what does he mean? What is the data? Make it more tangible. And I hope the previous examples already gave you some clue. But here is another categorization that I found useful. They say, well, at the very least, like the very lowest level, a data product, raw data is a data product. Like if you just offer data to somebody else, the fact that you offer that raw data, that can already be a data product in itself. But of course, a step up from that is derived data. So raw data could be, here's all the sales transactions. But the derived data could then be, this is the revenue per month, right? That's let's say a next level data product. And then decision support, that is okay, based on what we see, based on the revenue and the transactions we see, these are the actions you should take. So actually, I labeled those examples. So think raw data. What is raw data? Google Analytics is raw data. Salesforce data, ERP data, Bloomberg. Bloomberg can be a source of data. Weather, like any data you can think of can be a data source, right? And then derived data is more things like customer segmentation, a customer 360, where you try to build a full view of the customer based on all the data you have. Some finance KPIs that you want to track, sentiment analysis, that's all derived data. What is an algorithm? It's quite obvious that some things like churn prediction is an algorithm, right? I have some raw data, I might combine it with some derived data. I see the customers who left our company in the past year or who canceled the product or canceled the subscription. And then I'm going to try to understand what made them cancel the subscription. And then based on that, make predictions of our current customers who will also, which ones are most likely to churn. That's an example of an algorithm. You could also see that as a data product. Next product to buy is another algorithm, predictive maintenance and so on. Then as decision support, that's more an advanced data product. You could offer them a finance dashboard or operational performance dashboard or a real-time traffic map. So it's basically a high-level overview of insights that are going on in your company in order for you to make decisions. So it supports you in making decisions. But then as the automated trading example, automated buying and selling of stocks that I shared, the next thing where you want to go is automated decision making, right? Like a route planner, you could see that as a form of automated decision making. You just say to the route planner, I want to go from A to B. And then the route planner decides, okay, based on current traffic patterns and based on speeds that you can get, I think the shortest route or the fastest route from A to B is this. Spam filtering or targeted advertising is another example of automated decision making. All right, so I hope that gives you a bit of an idea when we talk about data products, what that is. So if you end up in an organization after your studies, I think that should be first and foremost in your head. Like, what kind of data products can I build here? What is the business doing, and what kind of data products can support the business in making better decisions? And it could be any of these, right? Any of the examples that I just described. And now let's zoom into how these data products are being created. If you take a big picture here, I think there is a pyramid of need in data analytics. So businesses aim to achieve the top of the pyramid, but in order to reach the top of the pyramid, you need to satisfy the below layers. So it's a bit analogous to the Maslow pyramid of needs, where like on the top of the Maslow pyramid of needs, everybody wants self-actualization. But in order to get to self-actualization, you need to have a sense of belonging first, and food and shelter and all of these things. It's the same with data analytics, and the pyramid looks a bit like this. So at the very top of the pyramid, everybody wants data insights, right? Everybody wants to create insights that has an impact on business. But in order to create those insights, in order to deliver that, you need to be able to build data pipelines. You need to be able to build reliable pipelines that can ingest, combine, and aggregate data and organize data from different sources. And now, if you want to have that skill of building data pipelines, you need to have your data operations in place. So you need to be able to handle workflow management, monitor job execution, measure data quality, automate deployments. And you see, like, the lower we go into the pyramid, the more technical the story becomes, and the more engineering focused the story becomes. And then finally, if you want to have data operations, of course, it needs to run somewhere. So it needs to run on some kind of data infrastructure. So maybe a data warehouse or a data lake or a real-time event hub or whatever that is, but you need some base infrastructure, right? Now, the paradox here is that the business value is clearly on the top. You get your business value by creating data insights for your business. That is obvious. But the amount of work that you need to do is at the bottom. So just managing and building and creating data infrastructure is a lot of work. And we're going to see later how that's being made easier these days. And then operations also a lot of work, and data pipelines as well. And what we see in a lot of the projects we do at companies, there's often a machine learning component, but the machine learning component takes like 10% of the time, or maybe 20% of the time, where 80% of the time of the data team is spent on these bottom layers, right? And well, later down the course, we're also going to share like the data infrastructure part. I believe we're big fans of doing that in the cloud. Why? Is because it takes a lot of the complexity away of managing data infrastructure. It's super, super hard if you do that on premise, and the cloud accelerates a lot of that. Now, as a simple dividing line, you could say that building data insights and building data pipelines, that's all part of your data product, right? Because every data product you create, you need to create your own pipelines, you need to create your own insights. While the operations and infrastructure, that is part of what I would call a data platform. Why? Is because you only need to create that once. Ideally, you have one data platform, and then many data products are built on top of that. There are also organizational aspects to this, about how you organize yourself in multiple teams, so multiple teams can build multiple data products and as much as possible reuse the same data platform, but we won't zoom into that today. So this is just about more the technologies behind it, but be aware that in large organizations, if you see this, there's also human scalability issues sometimes that we've seen companies building, for every data product they build, almost built their own data platform, so you have like 6 silos right next to each other. Obviously, that's not very healthy, that you waste a lot of effort, and typically you lose a lot of data governance as well. We've also seen the opposite, where there's one central department who says, so we're going to do everything, we're going to build all the data products ourselves, we're going to build all the data platform ourselves. And then you have this central monolith that is always the blocking factor in an organization. So that is also not very healthy, right? But anyway, regarding the organizational aspects at the moment, let's look into it a bit deeper. So if you look at how a data product is actually being created, we always see the same 4 phases coming back. So it always starts from some kind of experimentation, where you run some ad hoc queries, or you run some notebooks like a business person comes with a need to you, say, hey, we want to get insights into this, and you just start hacking around, playing around to see if you find a pattern, if you find an algorithm that works for you. If you've proven that you found such an algorithm, then you go to the next phase, which is the implementation phase. And now not every data product goes there, right? So you could say, hey, here's a business demand to build a self-driving car. Well, actually, you need a lot of experimentation and a lot of analytics development before you can even have a proof of concept of a self-driving car, right? Before you industrialize it and implement it and deploy it to 1 million cars out there, right? So, but typical data products are less complex than that. So they go from an experimentation phase to an implementation phase. And there, that step is often overlooked, right? Sometimes whatever organizations have in the experimentation phase, they just put that in production and they use that. But that proves to be very unstable. And why is that? Is it because once you want to industrialize an algorithm, you need to start following best practices. You need to start building modular data pipelines, things like that. Is very boring engineering practices, but it's a bit similar to if you build a prototype car for a car manufacturer. That's all nice and well, and it can prove a market or prove an idea, but you don't mass produce cars in the prototype garage either, right? So it's the same with data products. It's cool that you have an experimentation phase, but then when you go to an implementation phase, there's some other procedures that you typically follow. Once you've done that, once you've implemented the data product, it's fine that it runs on your laptop, but your laptop is not part of, let's say, the big deployment or the big environment where it needs to run. So you need to at some point go into a deployment mode where you take what they call artifacts. You need to take these artifacts and deploy them to an environment and also manage all the governance around that. And then finally, once it's out there, you also need to monitor this. There's a lot of data pipelines that crash all the time. It's a lot of instability. Also, your infrastructure can be unstable, so there is a monitoring phase. Now, not everybody is as mature with this, and by the way, we make mistakes against this as well. So I'll give you a very simple example. If the only thing what you have is Excel, you could use Excel just to go through all of these 4 phases, right? So you could start with just playing around with Excel and hacking around until you have like a pivot table that you like in the experimentation phase. Then in the implementation phase, you separate it more out into clean tabs, and you make sure that everything is a bit structured and organized within your Excel. Then deploying is just you put your Excel on a shared drive to share it with everybody else so they can get the insights as well. And then monitoring is more that if you enter new data into Excel, that it doesn't break any of your calculations, right? So it's not related so much to technology. It's a process that all data products go through. Luckily, we don't see a lot of Excel data products anymore. When they talk to us, it's usually about industrializing them in a more sustainable manner. What we do see is a lot of notebooks that once the experimentation phase is done, that they put them in production directly. We are very, very much against it because we see a lot of things going wrong there. But anyway, it really doesn't really matter which technologies you use. You always go through these 4 phases. Right, I hope that makes sense. Maybe one more thing to add on this slide is that on the right-hand side, what you see here about experimentation and implementation, that's if you map it back to the pyramid I just showed you, that's building data products. On the left-hand side about deployment and monitoring, that's all about building data platforms, right? The left-hand side, you should ideally do only once. You should only do once, set up your deployment mechanism, set up your monitoring mechanism. While the right-hand side, experimentation, implementation, you should try to do as many times as possible, as quickly as possible, right? This is a cycle, so you go through this with every data product that you build. You start with experimentation, you implement, then you deploy on your data platform, then you monitor it. The question I sometimes get from clients is, well, how fast should I go through this cycle? And like the first data product you create, maybe it takes you 3 months to get through the full cycle because you have to set up everything for the first time. But after that, you should try to be able to speed up the rate of deployment. And how far can you go with this is that there's, I always tell people you should aim to have 10 deploys a day. If you have more than 10 clients a day, which other companies have been doing that for a decade, you'll also be able to learn from your customers from feedback 10 times a day. On the other hand, if you can't deliver new software at least every 2 weeks, then don't call yourself agile. That might be a bit an abstract notion for you guys, but in the enterprise world, there is this big hype around being agile, where they work in 2-week cycles or something like that. But very often, what they forget is that they actually have to deploy at the end of the 2-week cycle. So they deploy still once every 3 months. That's not agile anymore. Anyway, that's not the topic of this talk. If you want to know more about that, there's a good book being written called The Phoenix Project, and it dives all into how to be agile and how to apply what they call DevOps best practices in this world. All right, maybe one more thing I want to give with that is I talked about data products. I didn't talk about data projects. A data project is very much like building a bridge. And that's an oversimplification still, but when you want to build a bridge, you set a goal like, hey, I need a bridge from A to B. You get funding for the bridge, you make a plan. For building the bridge, you hire some builders, you build the bridge, you test the bridge, and done. You open the bridge, right? That really is a very bad analogy. I see it a lot in data products or in data initiatives. And it assumes that everything is known up front. But that is not true. So instead of having this project mindset, try to adopt a more product mindset. And in a product mindset, you don't talk about requirements anymore, you talk about assumptions. And how can you validate those assumptions? You don't talk about we know, but you talk about we believe. And instead of always saying, let's build it, no, let's test it first. So an example there is, I could say like, hey, as a requirement, I need to have automated discount calculation based on the person who visits our website, something like that. You could say, well, that's a requirement, but what is the underlying assumption? And the assumption is like, hey, if we can do targeted pricing or tailored pricing to the unique customer, then we're going to get higher revenue. Okay, how can we test that assumption then? What do we believe? What do we believe for that assumption to be true, and how can we test that assumption? Again, this might sound obvious in theory. In practice, we still work a lot with organizations who have a lot of requirements and a lot of plans, and they don't test a lot. They don't validate their beliefs a lot. So if you go into the business world, try to think more in terms of products and less in terms of projects. That brings me back to one of the first things I said is like, as businesses become more data minded, their needs are shifting from traditional reporting to machine learning and AI. You can plot that on a XY axis, where on the X axis is technical maturity. On the Y axis, you see the value it often brings to organizations. And then you see this trend, I hope it's clear, from financial reporting to operational reporting, self-service analytics, and so forth to intelligent applications. Now, the point is that business need to make decisions more and more in real time and based on machine learning. The line also implicates that the line between operational applications and analytics environments is blurring. And that means that data platforms are evolving as well, right? So where it used to be that you had data warehouses, I don't know if you heard about the term, we'll discuss what they are. A data warehouse would solve all your analytics needs. That's not true anymore. After the era of the data warehouse, you had the era of a big data systems or Hadoop systems, things like that, where a lot of analytics happened on those things. And now the latest trend we see is that people move to cloud native systems. Now one doesn't replace the other, right? In a cloud native world, you still need a data warehouse, for instance. So it's a bit easy to put it on one chart like this and showing that one is better than the other. That's not true. It is true that data warehouses were mainly built to solve these kind of issues like financial operational reporting, while cloud native systems can go much broader than that. So let's step into those data platforms. What is a data warehouse? A modern data platform needs to deliver on the following capabilities to be successful. When people ask me to build a big picture of what a data platform is, it's always the same thing. It's data sources on the left, and that could be text data, databases, web data, mobile data, factory data, whatever. And there's some insights on the right. So that could be a dashboard, a mobile app, information for an operator, what have you. And there in the middle, you have a notion of what they call batch processing. So that means you take the data in and you process it batch by batch, so maybe once a day. You can have the same logic, but then in real-time processing, where you work with some kind of data broker that delivers you the insight. And these processing systems, typically you don't want to expose that to the outside world. So typically you build some kind of serving layer, what they call a serving layer, and that could be a database or an API or an alerting system that is kind of an interface between the dashboards that you create or the applications you create and all the data insights you build here. And then finally, a fourth component of a data platform is that obviously on that data, you have data scientists and data analysts who want to do their experimentation. So they can't be here on the serving layer because that's already aggregated data. That's not interesting for them. They want to be smack in the middle of a data platform. Now, what does a traditional data warehouse offer? It's more or less a subset of this. So a traditional data warehouse is very useful for ingesting structured data and building traditional reports. And then there's data science tools like SAS or SPSS that are often added to a data warehouse to create additional insights. So it's a subset of a total data platform, I would say, but still very valuable. How does it typically look like in IT terms? Well, imagine you have a few like very traditional databases here, like your CRM system or an ERP system or a billing system. They all get collected into one big database, and like the big database vendors are Oracle, Microsoft, IBM, these kind of companies. Here's all the data as landed, is aggregated together. Then you have these systems, what they call ETL systems. An ETL system is extract, transform, load. So it extracts data from a source system, it transforms it a bit, and it loads it into a data warehouse. And these systems make sure that they mold the data, they wrangle the data so that they can be used by reporting systems. Example ETL system is an SSIS, Data Stage Informatica. And the reporting systems, the more traditional ones, are like Cognos or Qlik. And then as I mentioned, more and more we see also data science systems like SAS and SPSS being connected to the data warehouse. Now, these in traditional BI and data warehouse world, very often they use like what you see here is a visual ETL tool for data processing. It's something you use that gives you a visual view of transforming data from source to destination. You join data, and it's nice to design a data pipeline like this because it's very visual. I take the data here, I flow it through the system like that, and then in the end I populate it like here. That works in a data warehouse world where you have relatively few data sources, but it becomes problematic if you scale. What you see now is that also data science tools, they also become more visual drag and drop. So you see here data being ingested, being aggregated, and in the end there is a logistic regression being applied to it. This is an example of Alteryx. And honestly, I really don't understand why they're doing this. Why on earth would you want to do your data science flow just like your ETL workflow in a visual way as well? Our advice there is you should just use code. So writing code, and has a lot of benefits. First and foremost, making predictions, it's not really hard anymore. Building algorithms to make predictions is hard, but there are a lot of these algorithms, they are packaged in libraries, so you can just use the library. So here you see an example of prediction of values using an algorithm called the random forest algorithm. Now, implementing a random forest algorithm is probably very hard. I don't need to implement the random forest. I just need to trigger a library that does the random forest for me. If you do that, if you write code instead of visual drag and drop tools, you win a lot more than just the code. Without going into the details of all of these, let me just say it's just far more reliable to do it in code than in visual drag and drop tools. And most importantly, like the best engineers and scientists that we work with, they all want to write code, right? So going forward, I think the future, I understand where it's coming from in traditional data warehouses, that you had a lot of visual ETL tools, visual drag and drop tools. I think and I hope that trend is going to go away for more coding tools. All right, that was a bit about data warehouses. Then the next system I'd like to discuss is on-premise big data clusters. And that's a trend that's going away now. But when we started Data-Minded, there was a lot of companies that invested heavily in this. So you can imagine a data warehouse is a server, like a physical machine that you put in a rack somewhere in your data center. But it had some limitations. Like at some point, like a single server couldn't scale anymore. And then there was this trend of big data clusters, Hadoop clusters being created. Hadoop is a particular vendor of big data clusters, and the nice thing is that you could ingest a lot more data in these traditional big data platforms. You could do a lot more processing on a lot more variety of data. You could handle a lot more data on these things than what you could in a data warehouse. The downside is that most of these weren't really able to do real-time processing, right? What it would look like is that instead of having a single machine, you would have racks and racks and racks of machines. It could be very expensive. I know of Hadoop clusters that had like at least 2 petabytes of data. So 2 petabytes is 2,000 terabytes of data. And I think there were like, I don't know, 100 nodes or something, or 50 nodes. And the nice thing is that it scaled very dynamically. So if you needed more compute, you just added a server to the rack and you could scale. The downside of this approach is that obviously you need a lot of hardware management, and that became very complex. So there were 3 big vendors of Hadoop called Cloudera, Hortonworks, and Mapr. They were sort of competing with each other. Now, Mapr has become more or less broke. They got sold to I think, HP, if I'm not mistaken, and Cloudera and Hortonworks joined. They became one company. They merged. So now you basically, if you're in the market for a big on-premise big data cluster, you basically have one company to go to, right? And the reason why it became so problematic, or why they had this, why they're going down again, is because you had cloud providers around the corner. one of and we're going to talk about cloud providers later, but one example of such a Hadoop implementation that we've seen is that, well, imagine you have many data sources here and you had a very big operational big data cluster. So this is a real life example that we worked with. That big data cluster interfaced with the data warehouse. And you had data engineers here maintaining and setting all of this up. It also provided several outputs, like operational outputs to the rest of the organization. But then the data scientists also wanted access to all of that data, of course. But the people here said, no, wait, that's an operational cluster. We cannot give you access to this because if you do something wrong, then you'll break it. And so imagine this is like 20 or 50 nodes or something. So what the data scientists had to do is they had to create their own cluster here and build a privacy gateway in between. And then the data scientists could do their own experimentation on the right-hand side here. And once they found their insight, had to hand them over back to the engineers. This entire process took like a year to set up or something. This was really not efficient at all, on the contrary. And that's one of the downside of these large on-premise systems. I understand there was a need for it at some point because the data warehouses weren't scaling anymore and cloud wasn't really an option yet. But I think going forward, I don't expect a lot of these systems will be built anymore. So that brings us to the cloud. I mentioned a few times already. I think the cloud is one of these big differentiators, and I don't know how much you've heard of the cloud. If you're not technical at all, you have used maybe Dropbox or you use Gmail or Hotmail or something. These are all services that are managed in the cloud for you. So you don't see any hardware somewhere. Some big organization has put some servers somewhere, but you don't see any of that. The same is happening in the data world where there's 3 big cloud providers at the moment. There's Amazon, there's Azure from Microsoft, and there's Google Cloud. And a lot of the data analytics that we see is moving into these 3 big cloud vendors. I sometimes get the question like, but is it such a good idea that 3 big American companies hold all the power and are used for all the data processing? Well, as a European citizen, maybe no, that's not ideal. At the same time, there's no real alternative at the moment, right? So between these 3 cloud providers, they're very good. You can do all the data analytics you want with it. It's a bit like buying another car. Like, do you want an Audi or a Volkswagen or a Ford? I mean, you can debate about it for hours, but they're all good cars, right? I do expect in the future that there will be some European cloud providers who are mature enough to offer their services. At the moment, so March 2020, we haven't seen any yet that are really successful. All right, so let's step into what we mean with a cloud native system. So if you look back at the data platform architecture that we drew earlier, the nice thing with cloud native systems is you can do anything with it. You can do real-time processing, batch processing, data exploration, data science, like a full serving. You can build whatever you want with it. There's many more technologies in those cloud systems than what you can build yourself. As I said before, at the moment, there's only 3 big cloud providers. So here's a trend that you see from 2017, 2018 to 2019, where you see actually there's 3 big ones. There's Amazon, Microsoft, and Google. And while in the past you had some smaller players, most of them have disappeared. Now there's some niche players like Oracle, or IBM, or Alibaba, but so far the 3 main ones are really Amazon and Microsoft and Google. Why is that? Well, a chart I really like about this is about what they call the trailing 12-month CapEx investments of the different cloud providers. I'll make sure my own picture is gone. Yeah, there we go. What we see here is that a trailing 12-month CapEx means how much have they invested in their own cloud infrastructure in the last 12 months. And then you see the 3 big ones. They're really investing 17 billion or 12 billion or 10 billion, which is a crazy amount of money to invest in 1 year, where players and they're even accelerating their investment, where other players like Oracle or IBM, they're only quote unquote investing $3 or $2 billion, which is a crazy amount of money, right? Don't get me wrong, it's a lot of money. But still, it's nowhere near the kind of investment that the others are making. So I'm a bit afraid that the other cloud providers, they're lagging behind in terms of investment, and it will be hard for them to catch up. Just a financial intermezzo to explain why these 3 are so powerful. I think this is one of the main reasons. And to put that into significance, in the last 12 months, Amazon and Alphabet's capex is almost 10 times the size of Coca-Cola, companies whose products are available in every grocery store, gas station, and vending machine in every town and country in the world. So that's insane, right? They invest 10 Coca-Colas every year and just into making their cloud more successful, which is pretty cool. What is cloud actually? Cloud is, so if you look into traditional IT, what you would get is you would have to do everything, right? I don't know if you've ever seen a data center up close, but it's just racks and racks of servers with networking connected to each other. And you as a company, you're responsible for everything. You're responsible for networking, for storage, for servers, for virtualization, for operating systems, middleware, runtime, data, applications, everything, right? You have to do everything. While in the cloud, the very basic offering in the cloud is what they call IaaS. IaaS is infrastructure as a service. So you just tell your cloud provider, hey, dear cloud provider, give me a virtual machine. And I'll try to open a tab here. Yeah. This is the Amazon console. And so here you can just go to EC2. EC2 is one of these services where you can just get a virtual machine, say, hey, launch an instance. It's going to ask you a bunch of questions, but in the end, this is some kind of tutorial or wizard where you have to walk through, and then you can shop for, let's say, hey, like this is a crazy instance here. I want an instance with 72 cores and 192 gigabytes of RAM. If I click next a few times, I will be able to configure this. Then it will take 5 more minutes for me to spin it up, and I will have a virtual machine. Now, for those of you who are not used to this is insane, right? If you do this on premise, it will take you sometimes, at best days, you create a ticket and a few days later you have a machine. But sometimes you have to go through procurement and it takes weeks and months to get this machine. Here on AWS, you get it within an instant. It's the same in Azure. If you go to the Azure home screen, you can also quickly create a virtual machine and spin it up in seconds, right? And the same in Google Cloud, where you say, hey, just add a virtual machine. So this is Azure, add a virtual machine and say what you want. You click next a few times and you have it, which is pretty cool. Right, that's just an example of what IaaS is. That's a virtual machine in the cloud. You get that in minutes. Now next is what they call PaaS. PaaS is, you don't even have to worry about the virtual machine or the operating system or whatever. You just manage about you worry about your application and data. An example there is just give me a database. I need a database with this version of my database engine with this kind of storage, and you manage upgrades, you manage security, you manage patching. And then finally you also have the notion of serverless, and serverless is where I don't even see the data anymore. I just call a function or I just trigger something and you manage everything. So an example of serverless is Google BigQuery, where you just send a query to a bunch of data and you get a result back, and you have no clue what's going on behind the scenes. You don't have to manage that. Google scales that for you automatically. And then finally, of course, you also have what they call SaaS, software as a service. For instance, your email provider, that's probably a SaaS. Like you don't even see the email application. When I open my Gmail, I don't see, I have no notion of the Gmail application. I open my browser, I go to gmail.com and it's there, right? So that's even less to manage. And that's the trend we see in computing, is that like in the traditional computing, there was a lot of investment going on here in traditional IT, but people saw like, hey, I'm losing a lot of time here. I'm spending a lot of investment in things that really don't differentiate us from competition. So more and more companies are going towards IaaS and PaaS and serverless. An example, here's another example of creating like that Hadoop cluster that takes a year to build on premise. If I want a Hadoop cluster on the cloud, I just run this simple command, say AWS EMR create cluster with a bunch of parameters, and bam, I have my cluster. So that brings you the notion of instead of investing a whole lot of time in infrastructure, you just run a command and you get a cluster. And you get the notion of a throwaway cluster. You spin up a cluster, you run your compute, and then you shut down your cluster again, which is really nice. Another example of this is called Azure Batch. Azure Batch is just, you schedule jobs, you say, hey, please do this image processing or this text mining job, and give me like every green square you see here is a computer, is a virtual machine, and just process it on this virtual machine. This series of virtual machines And the greens ones are already available, the grays are spinning up, and the yellow, they're in transition state or something like that. The nice thing again is that I just need to define a pool. It's all software defined. It's being created for me, and then it's all managed for me as well. And the really nice thing is that it can become very cheap. Like in this example, for less than $1,000 a year, I have a 40-core, 320 gigabyte RAM cluster running 4 hours every night. If you want to have this on premise, it will take you like 500 meetings to get there, right? So again, going forward, I think the cloud is the way to go. Because of these speed and cost efficiencies you get. Now, what I've just shown you is a bunch of individual services. You have to still combine it into one big framework, right? One big data platform. And I'm going to give you an example of a potential cloud-native data platform, which uses both cloud and open source components for a scalable solution. This is just an example, right? There's a million platforms I can show you, and in fact, like this architecture is not the architecture we're currently using anymore, but it's just an example of what a cloud-native architecture could look like. So to begin with, you have a storage layer. So on a storage layer, you have data coming in, and there in this architecture, we use Apache NiFi as a tool to ingest all of that data and land it in some kind of data lake storage called AWS S3. And S3 is one of these serverless services. You don't have to worry about it. You just say, store my data and store as much as you can. It's very cheap and uses, it does that for you securely and scalably. And then on the computation side and the processing layer, we use a bunch of services together. This is on the Amazon platform. We use AWS EMR and AWS Batch. So these are both two like large-scale compute services from Amazon, and we orchestrate that with Apache Airflow. So Airflow is one of these open source tools that can trigger, say, hey, now execute this job on EMR. When it's done, then use this job on AWS Batch and so forth. And then finally, we also use the Glue catalog to store all our metadata. So because we have, remember the variety problem where you have so much different data sources that it's hard to manage, the Glue catalog is one of these services that Amazon provides where you register all your metadata. So you can, even if you have hundreds of thousands of data sources, you can still keep track there of like where it is and what it's doing. And then finally, we also have like a more consumption layer where we use Amazon Athena, which is some kind of SQL interface that you can query the data directly. And we use Jupyter Hub, which is a notebooking service to do some experimentation. All of this is in the data platform. If you want to export data, we export data to any database they like, basically to relational database, to DynamoDB, to whatever. I'm not expecting you to understand all of these components, but it should give you an idea of in a cloud native architecture. The idea is really to combine many of these components together and to build it into a large-scale data platform. And these components evolve over time, right? Every day, these cloud providers announce new services. There's also services from not of these big three cloud providers, but more external services that you can also integrate. So this is a very rapidly evolving space, and it also makes it very exciting, by the way. There's also a bit about Docker. And in fact, I'm going to skip that because it's a bit, it's a bit technical, but just know that Docker and the Kubernetes ecosystem that comes with it is one of these new trends in software development in cloud native architectures. It's a bit technical to dive into right now, but the notion is that you just, whatever you build, like whatever algorithm you build, you can wrap it in a Docker container, and you can deploy that Docker container in Kubernetes and then attach an API to it or something like that. You can connect it to your website, and then you don't really have to worry anymore, like how many people are using your website, how many times you have to trigger your machine learning model. It just scales automatically for you. It's just one of these trends that you have to keep in mind. Docker and Kubernetes is gaining a lot of traction. So if you zoom out a bit, what do I think as the main technologies trends that are shaping data platforms today? If my clicker works, for some reason it doesn't show anymore. Just a sec. There we go. No, it doesn't show. That's too bad. So I'll show it like this. What do we see as one of the main trends? The only constant is change. Data infrastructure is still evolving at a rapid pace. So whatever I said today will not be valid anymore 5 years from now, and whatever I said 5 years ago is not valid anymore today. What is hot today, what I can share, is that a lot of PaaS services and serverless services are very popular. So I understand it's all new for you, but look into Google BigQuery, Azure Event Hubs, AWS EMR, that is gaining a lot of traction. Kubernetes is also, we see a lot of adoption of Kubernetes these days. And then even more and more SaaS offerings, like we haven't discussed it, but Snowflake or Databricks or complete SaaS offerings that are really helping in the data platform space as well. So this is hot today. It can change tomorrow or the next day, but some trends are persistent. So what we've seen over the last couple of years, so as companies mature in data, they invest more and more in automation. So in the beginning, you have some experiments that yield some quick results, and it's all nice. But in the end, companies choose to invest in technologies that can automate things away from them. And there's also a move towards higher level of abstraction, right? So instead of focusing on the lower layers and networking and storage and all of that, you really start to see more and more focus on building data products, less focusing on managing the infrastructure and the operational aspects of a data platform. Then what do we see as trends? So I think there will be more and more streaming analytics, more and more real-time analytics. We see that a lot of our clients, so now batch processing is okay for a lot of the use cases, but more and more streaming use cases are gaining more traction. I also believe there will be more and more what they call data intelligence these days. So because more and more departments are getting access to the data, you also need more data governance or better data governance. So we need to be more aware of what is the data we have, who has access to it, how are we dealing with GDPR compliance, stuff like that. I think there's going to be more innovation in that space. And in AI, I think more and more we are going to see the automation of AI, that a lot of the models already come out of the box. Neural networks can be pre-trained. You have transfer learning, where you can apply the learning of one domain to a different domain. And I think we're going to see more and more of that, where actually the role of like the pure data science aspects will diminish, and it becomes more and more engineering. Right. And then the final slide, and I don't know why my slide screen is acting up, but let's try here. The final slides, I want to go back to this pyramid of need that I explained in the beginning, that I think there's a pyramid of need in analytics, and all the organizations want insights. Everybody wants machine learning. Everybody wants dashboards. But in order to do that, you need to be able to build data pipelines. You need to be able to ingest data somewhere and combine it with other data. In order to do that, you need to have your operations in check. And in order to do that, you need to have data infrastructure. And remember the whole discussion about cloud infrastructure. And the paradox a bit is that the business value is in the top. So people or companies invest in data analytics because they want the data insights, not because they want data infrastructure. There's not a company in the world who wants infrastructure, but they all want insights. While the amount of work is definitely in the bottom, right? The amount of work to set this up is definitely on the operations and infrastructure part, so more on the platform part. The good news there is that, as discussed, like the infrastructure becomes easier and easier because clouds are automating a lot of that. Cloud, you can just take it off the shelf on the cloud and it's there. It's much easier than to do it on premise. While the data operations part is maybe more in flux, I'm expecting to see more out-of-the-box solutions there as well. By the way, we're also working on an out-of-the-box solution there. And I expect to see more improvements there. And insights and pipelines, yeah, so that's all about building the data products. The trend there is what we said is, I think more and more will be automated, more will be real time. And I think it's a matter of actually implementing them and aligning them with your business as well, so that they're actually being used day to day. All right, I hope this big picture made some sense to you guys, and I also hope I didn't lose you too much along the way. Yeah, so my name is Chris, I'm from Data Minded. Let me go back to my webcam. Yeah, here I am. Thanks for listening. I'm not sure if this was super useful to do it remote. Normally when I'm in the auditorium, I can kind of feel the audience a bit, see if they're following along or not. So this time I couldn't do that. I still hope it was relevant for you, and then I hope to see you in person soon. All right. Bye.